My name is Ching and welcome back to Data Structures in C++. First, we are going to review what we learned in the first lecture. A C++ program starts with preprocessing, which modifies the program according to the lines that start with the hashtag. The second step is compilation, which translates the program into an object file which the machine can understand. The last step is linking, which merges and makes an executable file to run. When we run the .exe file that the compiler creates, it will be loaded into memory. Usually, the compiler will allocate a chunk of memory to store the data in the machine instructions, or code. The big chunk of the part of memory is for your data, such as the data you need in your code to run. There are quite a few different kinds of data that we need to take care of. The first kind of data to be loaded into memory is global and static data. They get created when the app is launched and stay in memory until you quit the app. Now, what other variables do we have to store? Let's start with dynamic variables. They are stored in something called the heap, which we will talk about very soon. There's also another kind of variable called automatic variables. For example, function parameters or a regular integer that you create. They're both growing in the variable space. Now let's take a look at what a stack looks like. A stack is basically a bunch of variables stacked on top of each other. So think of it as a stack of plates. You can only put plates on top of the stack, and you can only take plates off the top of the stack. And all of them must be taken off after they are put on, like how variables in the stack follow the entry and exit of code scope. But why do stacks apply to the parameter variables and automatic variables? Let's just think of parameter variables for now. On the right side, let's imagine that every green line is a function. The outermost function is called the main entry. So this is going to be the main function and we'll pass in some arguments, which will be the first thing that you put in the stack. Then the main function will call another function which will pass in some other parameters. The parameters will continue to be pushed to the stack until here. And this is where the innermost function exits. At that moment, the most recently pushed parameters will be popped out. And then the next parameters below get popped out and so on. Next, we're going to talk about the heap. Like we explained, variables in the stack follow the entry and exit of code scope. But what about variables in the heap? They're actually independent of code scope, which means they stay in the memory throughout the whole life of your program until you decide to destroy them or your program quits. When we talk about the heap, this term is overloaded. That means it has two totally different meanings. On the left side, we see the heap in memory, which is used to store dynamic variables. But later in this course, we will learn the heap as a data structure. This kind of heap is a tree where it maintains the biggest value at the top, and each subtree is also a heap. We talked about how memory is managed for different types of variables. Now let's talk about how the memory is indexed by something called an address. Let's assume the memory is a contiguous array of bytes, each byte containing 8 bits. Then we can assign a unique index value for each byte, starting from 0. On the right side, it is a piece of memory holding some C++ integer data, with each integer taking 4 bytes or 32 bits. We know what memory addresses are, but the most powerful feature of C++ is called a pointer, which can address memory directly, unlike Java. Let's see how to use pointers in C++. For the first statement, we make an integer called I. Then for the second statement, we define a pointer IP by using a star following the integer type. Next, for the third statement, we get the address of I using the ampersand symbol before the I. This address is then assigned to IP. Finally, for the last statement, we assign 100 to the variable that IP is pointing to, which is I. By using a star before the pointer, it gives you the variable at this address. This is called dereferencing. The below diagram shows the memory state where the variable I is at the address 456FD4, and IP holds that exact address as its value. So a pointer is simply a variable which holds another variable's address. Let's talk about the difference between object creation in Java and object creation in C++. In Java, we assign a student S to be a new student, and we put parentheses after student. In C++, though, we say student and then a star. S is equal to a new student. The result is still exactly the same in memory. Let's now take a look at the difference between creating dynamic variables and creating automatic variables. Dynamic variables, we use the new operator and a star to show that it's a pointer. On the other hand, for automatic variables, we just say the data type followed by the variable name. Now, we know how to create dynamic variables in C++, but how do we release that memory? In C++, we use the delete operator to release the memory from the heap. Please note, to delete an array from the heap, the delete operator is followed by a pair of square brackets. On the other hand, Java uses a method known as garbage collection to automatically release memory. Here's some common mistakes you might run into while you're dealing with the delete operator. First, you must initialize the pointer before you delete it. Second, if you assign a pointer to the address of an automatic variable, meaning a piece of memory from the stack, you cannot delete that pointer. In summary, you can only delete a piece of memory from the heap. Earlier, we saw that the way to access content from pointers doesn't look very comfortable. So there's an easier way to simplify that. Those are called references. References are basically aliases or names for another variable. In this example, IR is a reference of I, which means IR is an alias of I. In memory, there are simply two names of the same piece of data in memory. So regardless whether you modify the value of IR or I, you modify the single piece of data at that memory. But there's one thing you need to pay attention to, and that is, once a reference is associated with a variable, it cannot be assigned with another variable. That's because you already gave an alias to the variable, and you can't give the same alias to anything else. This feature comes in handy when you pass in a variable as a parameter to a function, where you can modify the variable's value inside the function, instead of just modifying a local copy of it. There are two operators which we can access the member variables or functions inside an object. You can use the dot or the arrow. The dot is used when the type is an object instead of a pointer to an object. For pointer type, use the arrow sign to access its members. Of course, you can always use dereference operator to get an object from a pointer. In that case, the last two statements are equivalent. Here's a summary of operators for the pointer type. The star operator is used for pointer definitions and also for dereferencing. The ampersand operator is used to find the address of an object, or can be used to create references. The new operator is used to allocate memory in the heap. The delete operator is used to deallocate memory in the heap. And last of all, the arrow operator is used to access content from the pointer, but you can also use the dot operator too. Here is an exercise to see if you understand how pointers work. First, you create an integer I, which is equal to 10. Then you assign the address of I to an integer pointer p. Now, we print out I, which is equal to 10. Then we print out the address of I. But because p holds the address of I, it should print out the same thing as the address of I. Then we use dereferencing to get the value of I. Finally, we print out the address of p, which is independent of the address of I. Have fun and happy coding! Bye bye, see you next time!